Okay, hello everybody. I'm Massimo Pascale. I am a last year graduate student at UC Berkeley. Today I want to talk to you about the Sunburst Galaxy, which is a galaxy at redshift 2.4, which I know compared to all the other galaxies we've been talking about is quite low redshift now. But I want to convince you why, if you're interested in sort of the star-forming high redshift JWST galaxies, you should really also be interested in the Sunburst Galaxy. And so it's sort of a 10 to the 9 solar mass Lyman alpha emitter. But what makes it so special is that it's beautifully gravitationally lensed. You can see it sort of sweeping out a partial Einstein ring about the foreground cluster that lenses it. It's one of the most spectacularly lensed galaxies on the sky, and it hosts a number of these star-forming clumps that you can actually make out from one another, right, because of the gravitational lensing effect resolving them. And so something that got this a lot of attention initially is that it hosts a bright clump, 22 magnitudes AB in the stellar continuum, that's leaking Lyman continuum flux. So you can see in the upper right corner, that's a filter that's sensitive only to the ionizing flux, and you can see the rest of the galaxy drops out, and you just see this knot, which has been multiply imaged 6 times. And so when you do the SED fitting from photometry and things like astrometry to get the size, the physical picture of what's going on becomes clearer. This is some very high density superstar cluster, 10 to the 7 solar masses, all contained within about 10 parsecs. And so this stellar surface density is reminiscent of what we're seeing in a lot of these high redshift JWST objects, right? Things like the cosmic gems or the cosmic grapes, hosting these young, high stellar surface density clusters. And so when we move to the spectrum, I think this is where this becomes the most interesting. So it hosts these signatures of massive stars, things like carbon 4p Cygni, as well as broad helium-2 in emission, maybe as signatures of very massive stars, cluing us into a young age, right? First couple million years must be for the superstar cluster. On the ISM side, we see these high ionization UV lines, things like carbon-3, oxygen-3, and crucially, strong nitrogen-3. And so this line has come up sort of a number of times in these high redshift JWST galaxies where we see either nitrogen-3 or its higher ionization counterpart, nitrogen-4, right? In these high redshift JWST galaxies. Whereas when you look in the local universe or low redshift universe, these lines in a star formation context go basically unseen, right? There's very few exceptions. And so we almost never see it in the local universe. We see it, it's rare in the high redshift universe, but we do see it. And then here it is in the most spectacularly lensed galaxy at cosmic noon. And we can localize it to an individual superstar cluster within this galaxy. We have IFU spectroscopy that allows us to do that. And so doing global photoionization modeling with Cloudy as well as BPAS, we can start to characterize this physical picture, which I've put up here in a cartoon. So we have some superstar cluster at the center. It's quite young, a couple million years old, very massive, very compact. It's about SMC-like metallicity. It's surrounded by populations of nebular clouds, and we infer that the nebular clouds are very highly pressurized, high-density nebular clouds. We infer 10 to the 5 per centimeter cube for the electron density. And likely, we think that this is pressurized by some combination of either the radiation pressure from the stars or the RAM pressure. Both are sort of the order that you would need to pressurize these clouds. And we can leverage these ISM lines to actually get out the gas phase abundances. I'm going to particularly focus on that nitrogen-3 line and the N over O that we derive for this superstar cluster within this galaxy. And so you can see here I've plotted the N over O. It's in that blue square. And it's significantly elevated compared to what we see in like local H2 regions. That's the black. Or in the green, these could be low metallicity star-forming dwarfs from the Galaxies survey. And it's actually somewhat similar to what we see in G and Z11. I know it's really small, but it's this light blue pentagon up there. So we see very similar N over O. And sort of wrapping this all up and putting this in perspective, right? In these high redshift JWST emitters, we don't always get the luxury of being able to resolve out all the individual components of this galaxy. But here at cosmic noon, because it's very bright, because it's gravitationally lensed, we're able to localize this to an individual star cluster that's very young, it's quite massive, and it's compact. And so I think all of the circumstantial evidence really comes together to point towards what could be causing this elevated N over O. I think the most natural explanation is that, of course, you have retention of your massive star ejecta, right? The CNO-processed material from massive stars is making their way out of the stars. This could be through rapidly radiatively cooled, fast line-driven winds. This could be a slower wind process, something like non-conservative binary mass transfer or very massive stars. That's either mixing with the ambient ISM, or maybe it's condensing and making up entirely these nebular clouds that are significantly enhanced in nitrogen. And so I think that this could serve as a perfect analog for what would be going on in some of these high redshift JWST nitrogen emitters perhaps they're also hosting these superstar clusters that are effectively retaining their massive star ejecta, and that's the emission that we're seeing. Thank you, everybody.
Thank you. So I would like to thank again all the speakers of the second part of this morning session. And now we break for lunch, and we reconvene at 2 o'clock.